2-3 proofs for you, the degree counting part. So our claim is that for a tree with n greater than or equal to 2 vertices, that the number of leaves is equal to this expression. So remember, a leaf is just a vertex with a degree equal to 1. Let's give ourselves some notation and refer to the number of leaves as L. So we want to show that L is equal to 2 plus the sum of the degree of the vertex minus 2 over all the vertices whose degree is greater than or equal to 3. So whenever you're doing these degree counting proofs, a good starting point is the handshake lemma. And that just states that 2 times the number of edges is equal to the sum of the degree over all the vertices. So one thing we can do right from here is split up this summation into 2 summations. So notice all we're doing is we took the original summation, which summed over all of the vertices, and we split this up into summing over all the vertices with degree equal to 1, and summing over all the vertices whose degree was not equal to 1, in other words, greater than or equal to 2. This is really useful because we're trying to find a quantity for the number of leaves, and remember, leaves are just vertices whose degree is equal to 1. So in other words, in this summation, we're just counting 1 for each leaf. So this entire summation is just equal to L. So this is a much nicer thing to work with because it's getting us a little bit closer to what we're trying to prove. Now we've introduced L in. It's not quite like what we want to show though, because this summation is missing the minus 2 part. Ideally, we'd like to just stick in the minus 2 over here so that our summation looks a bit more like what we're trying to show. However, we can't just stick in the minus 2 just because we feel like that and still maintain this equality. So we have to compensate for making this change. When we made this change, we subtracted 2 for every single non-leaf. So we can compensate for that by adding back 2 for every single non-leaf. And remember, if there's L leaves, then there's n minus L non-leaves. So by doing this compensation, we've maintained our equality, and this statement is still valid. Now we can go ahead and tackle this new part that we added. One thing we can do is we actually know something about this n because we know that we have a tree. For a tree, n, the number of vertices, is just equal to m plus 1, the number of edges plus 1. After making that substitution, we're left with this expression. So let's go ahead and expand and put the 2, carry it out. And this is really nice because then this 2m and this 2m go ahead and cancel each other out. And then we can also go ahead and combine this L and this minus 2L and go ahead and bring all the terms to the left side. All right, we're getting closer. Let's also bring this 2 to the left-hand side so it looks a bit more like what we're trying to show. And we are almost there. The only thing left between what we've proven so far and what we're trying to show is that this condition in our summation has degree of the vertex greater than or equal to 2, while the thing we're trying to show has degree of the vertex greater than or equal to 3. So can we go ahead and just swap this 2 out for a 3? Turns out we can, because notice when we're doing our summation, we're summing the degree of the vertex minus 2. So whenever the degree of the vertex is equal to 2, we're just going to be summing 2 minus 2 equal to 0. So we can swap this 2 out for a 3. To see it explicitly, all we're doing is splitting up the summation into degree of the vertex equal to 2 and greater than 2. And notice that if we substitute in degree of the vertex equal to 2, we get 2 minus 2, which is just 0. And instead of bothering to add up a whole bunch of zeros, we can just ignore this first part of the summation and go ahead and swap out the summation for the only part that actually adds anything. Awesome, and this is what we wanted to show. So to summarize all the steps we did, we started off with the handshake lemma. We split up the summation, which was useful because it introduced the L term in. Then we modified our summation so it would have the minus 2, and we had to compensate for our modification to the summation. Then we applied the tree property, the fact that n is equal to m plus 1. You could have also equivalently worked on the left-hand side and used m is equal to n minus 1. Then we expanded and combined like terms. That simplified a lot. And the very last step was to do a change in our summation condition, switching out this 2 for a 3, noting the fact that whenever the degree of the vertex is equal to 2, we aren't actually adding anything. Okay, so a common question here is, how was I supposed to come up with all these steps? There's no way I would have known what to do after doing each one of these steps. And the good thing is, you aren't expected to know exactly what to do for some of these degree counting arguments right from the start. What you are expected to do is try things out. So go ahead, try applying the handshake lemma, try applying properties you know from the problem. In this case, we knew we had a tree, so that allowed us to substitute some things in. And it won't be like a straight linear path. You might end up with some dead ends and some invalid manipulations before you eventually get to the right answer, and that's totally okay. And you'll get a lot better and a lot faster with practice. Best of luck!